Welcome back. In the last couple of videos, actually the very first video on centripetal acceleration, I told you that the necessary centripetal acceleration, and we're just talking about the magnitude, and actually the c tells you the direction, right? It's centripetal, so it's inward acceleration. It equals the velocity squared over the radius. And I told you that the real rigorous proof has to be done with calculus, but I looked on Wikipedia and there was actually a pretty neat proof. Although when you read Wikipedia, it's not so obvious on what they're saying. So I thought I would do a video on it because this is cool and you don't need calculus to understand it. So let's just do something and let's just plot the distance vector, the velocity vectors, and the acceleration vectors as something goes around a circle. So let me draw two circles. So let's say this is my first circle. Let me draw another circle. I'll do another color just for fun. Okay. This is my other circle. This is the center circle. And this is the center of the circle. And so what's the position vector at any point in time? Well, the position vector, you could kind of just draw it as a radius. So the position vector at any given time looks something like this. So let's say initially this is the position vector. That's the initial position vector. Its magnitude is the radius of the circle. And its direction is, well, I guess right here, in the positive x direction. And then at that point, what is the velocity vector? Well, the velocity, let's assume we're going counterclockwise. I don't know why I assumed that. It could go the other way. Let's say this is the velocity vector at that point. The velocity vector is going to look something like that. That is the velocity vector. That's v. Right? It's going tangent to the circle. Well, let's plot that same. Let's plot the velocity vector as a function of time on this circle. So if that's the velocity vector at that time, I can draw the velocity vector here. This is the same vector. Remember, I'm just saying at a particular time, what does the distance vector look like, and what does the velocity vector look like? So at that time, the velocity vector looks like this. And I'm trying to make it the same size to show you it's the same vector, and I'm doing it in the same color to show you it's the same vector. Right? This is the exact same vector. This is the actual circle. Like if you were to draw it, this is the path of the dot or whatever is moving around the circle. And this is, you could just kind of view it as I'm plotting the velocity over time, the velocity vector over time. So let's draw, let's say a few seconds later, or a few moments later, what does the radius vector look like? Well, then the radius vector looks like this. The radius vector looks like this. I'm trying to draw it as neatly as possible, just to. And what does the velocity vector look like? Go back to the purple. The velocity vector, once again, is tangent to the circle, and it'll look like something like that. It's going to have the same magnitude, just different direction. So, actually, let me do it in a different color, just to show you what I'm doing. So let me do it in brown. So the velocity vector is going to look something like this. That's a brown. It's supposed to be a brown. That's the velocity vector. So after a few seconds or a few moments, where's the velocity vector here? Well, it's going to look like this. And remember, this vector, I'm just plotting it here after a few seconds. So let me make sure I got the line tool. So it's the same magnitude, and now the velocity is just at a different angle, and it should be the exact same angle as what I just drew in the other circle. Right? And I'm going through, so that's this velocity vector. Right? So when we start here, the velocity is going tangent to the circle. After a few moments, the object's rotating around the circle, so now the velocity is the same magnitude, it's just switched directions. And so what's happening here, when we plot the velocity vector over time, it has the same magnitude, so it'll draw out a circle, but its direction changes. So what is, just as in this case, what takes us from this point to this point, this was the velocity vector, and the velocity vector is always changing. But in general, this is the change in position. And what causes the change in position? Well, the velocity, or at least the speed, because the vector is always changing. So in this case, what's changing the velocity? Well, just like velocity changes radius, acceleration changes velocity. Right? So let me draw an acceleration vector. And the acceleration is going to be in this direction, right? Because if the velocity is changing from here to here, the acceleration is kind of going along the direction of the change in velocity. So the acceleration vector might look something like that. It's going to be tangent to this velocity path. Right? And that's interesting too, because if this is the acceleration vector when the velocity is here, so when the velocity is here, the acceleration vector is going directly to the left. So then that means that the acceleration vector is going directly to the left. And so this is also the acceleration vector, which it coincides with what we learned about centripetal acceleration. The acceleration has to be going inwards. And we see that when we actually plot the velocity vector. And if we plot the acceleration vector here, once again, it's going to be going tangent to this plot of the velocity vector. Well, let me do it in a different color. I've already used that color. I'll do it yellow. So then the acceleration vector is going to look something like this. Remember, acceleration is nothing but change in velocity. So at this point, when this is the velocity vector, the acceleration vector will just be this. And once again, it's just in the opposite direction of the position vector. So why am I doing all of this? Well, I'm doing all of this to set up the analogy, to show you, as this object completes one entire path, what's happening on this circle? Well, this circle, the velocity is completing one entire path, right? However long it takes to go around this circle is the same amount of time it takes to go from this velocity back to this velocity, right? The magnitude is the same the whole time, but the direction is changing. So if this takes 10 seconds to go around the circle in real position, then it takes 10 seconds for the acceleration to change the direction of this velocity enough that it goes back to the original velocity direction. So why am I doing all of that? Well, how long does it take for the object to do one rotation around this path? Well, it's just the distance divided by the velocity, right? So the time to do one revolution around this path is the distance. Well, that's just the circumference of the circle. Well, that's 2 pi r divided by your speed, which is v. And so, how much time does it take to go around this path? Well, we know it's going to be the same time, right? And now we're going to say the time is going to be the change in velocity, right? Here in this circle, this is the change in distance, but it's the change in velocity. So here we had this much change in velocity. I know this might be a little bit non-intuitive. Then we have a little bit more change in velocity, a little bit more change in velocity, a little bit more change in velocity. So the total change in velocity is just is the circumference of this circle. And what's the circumference of this circle? Well, the radius of this circle is the magnitude of the velocity. So it's 2 pi times the velocity of the circle. And so what is the amount of time it takes to do one revolution? Well, it's the total change in velocity, and that's 2 pi times the magnitude of the velocity, divided by acceleration. And if this doesn't make complete sense, you just remember, acceleration is change in velocity over change in time. And it's a little I'm glossing over a little bit because you might say, oh well, the net change in velocity is 0, but we're actually more concerned about kind of what's the total change in the velocity. So it changes a lot and then it goes back to its original so that the net is still 0. But this should hopefully give you a little intuition. So think about what I said, but the bottom line is we know that this expression and this expression have to be equal, because in the same amount of time it takes the object to do one complete revolution on this circle, its velocity, direction, has also done one complete revolution. So we can set these two equal to each other. So we could say 2 pi r over v is equal to 2 pi v over a. Let me switch colors. We can cross the 2 pi out on both sides. And then we could multiply both sides times v. You get r is equal to v squared over a. Multiply both sides times a. I'm doing this a little bit circuitously. And you get ar is equal to v squared. And divide both sides by r, and you get a is equal to v squared over r. So hopefully that gives you a little bit of intuition about why this works. And I got this from Wikipedia, so I want to give them proper credit. And hopefully my explanation helps clarify what the people on Wikipedia are talking about a little bit. Anyway, I'll also do the calculus proof, because that's kind of more, just straight up math. And I'll see you in the next video.